Say you were on a ship. Amidst your expedition, your ship bumped into a solid object in the sea, leading for it to have a hole. For your ship, however, such wouldn't be a problem, since there's a partition to stop the water from flowing into the areas of the ship, right? But that's not the case. The ship continued to sink as time passed. You realize that when the bulkhead with the hole has filled up completely, the next bulkhead will also start to flood, much like a domino effect. Knowing this, you induce that the ship which you had believed to be very formidable will still sink given enough time. Trusting your induction more than the ship, you manage to prepare yourself and so you survived. This kind of event is what happened in the sinking of the Titanic. It is also a basic concept of mathematical induction. And just like how we proved that the boat will sink using our two pieces of information, we will also be proving other cases in this video. Mathematical induction. Mathematical induction is a mathematical proof technique used to prove if a formula, theorem, or statement is true for every natural number. To prove, you must follow three simple steps. First step is the base case. You must check if the proposition n is true for n equals 1. Second step is the induction hypothesis. You have to assume that the proposition n is also true for n equals to any positive integer. Third and final step is the inductive step. You need to prove that the proposition n is true for n equals to any positive integer plus 1. To understand it more clearly, here's an application where we can use mathematical induction. Tower of Hanoi is a puzzle or logic game in which the participant use 3 vertical pins and a set of donut-shaped discs of different sizes. The objective of this game is to move all these from the initial to another pole without breaking the 3 rules. 1. The player can only move one disc at a time. 2. Only the top disc can be removed. And 3. No longer disc can be set over a small disc. The main thing you need to remember to solve this puzzle is first, you need to move n-1 disc in the second pole. Then move the bottom disc to the third pole. And we again move the n-1 disc in the third pole. And that's it. Now we need to know how many moves it requires to finish the puzzle with n disc. To move one disc, it only requires one move. To move 2 discs, you need to move the smaller disc first, then the bigger one, and lastly the smaller one again, with a total of 3 moves. To move 3 discs, we need to move the 2 discs first, and we know that moving 2 discs requires 3 moves. Then we have the bottom disc, and lastly the 2 discs again, total of 7 moves. And so on. Suppose we want to move n discs, let us first call the number of moves required to move n-1 disc m of n-1. Then we can form the equation for solving n discs with that. We move n-1 disc twice, plus 1 move for moving the bottom disc, and we can call this m of n. By analyzing the chart, we can say that to move n disc, it requires 2 to the n minus 1 move. Based on our analysis, to move n disc, we need to move n-1 disc twice plus 1 disc. But we want to compute the number of moves directly as a function of n, and our claim says we can do that. The number of moves is 2 to the n-1. But is this equation true for all n? How can we prove our claim is true? This is where induction takes place. The first step in induction proof is to prove the base case. Prove that the equation is true when n is equal to 1. We just have to substitute 1 to n and solve. 2 raised to 1 minus 1 is equal to 1. And we know that to finish this puzzle with one disk, it only takes one move, thus P of 1 is true. Now let's proceed to the next step, the inductive hypothesis. We just need to assume that the P of n is true for any positive integer, and we can write it like this. Last step is the inductive step. In this step, we will prove that P of n is true for any positive integer plus 1, and we can write it like this. Based on our analysis, and able to solve this puzzle, we should first move the n-1 disk, which we call m of n-1. Then move the bottom disk, and move the n-1 disk again. So that's 2 times m of k plus 1 to move the bottom disk. Then we can substitute what we assume in the inductive hypothesis. To finish it up, we'll just do a little bit of algebra. Distribute the 2 times 2 to the k is 2 to the k plus 1. Negative 2 plus 1 is minus 1. And that's it. We finished the proof. Credits to the following.